Hello, this is the Midterm 1 review for Math 2B at UC Irvine. This is being brought to you by Lumist, which is an education platform providing accessible academic support to both high school and college students. And Lumist at UC Irvine is a community for anteaters taking courses in mathematics, chemistry, physics, economics, and statistics, and so on. I'm Aaron Gennaro Stone, a new instructor at Lumist. Just finishing up my master's in statistics at the University of Waterloo. I did my undergraduate in quantitative psychology at the University of Manitoba. And a fun fact about me is that I enjoy fencing, specifically the sport, not the occupation. So by the end of this lesson, you should be able to find a generalized antiderivative for any function you're given, as well as you should be able to recognize and apply the most common integration identities. So during the original live presentation, I asked, as a little icebreaker, what professions actually use calculus in the real world. We got some answers in the chat box, which included engineering, as well as, I believe, economics, both of which, of course, are heavily dependent on calculus. For engineering, you might find yourself in the future taking courses in ordinary differential equations, partial differential equations, which very much utilize what we're about to learn. Most differential equations are solved, indeed, by means of integration. It's going to follow from some of the theorems we're going to learn today. This relation between integration and derivatives, which you already know. So one interesting application is, of course, for me, and it's kind of how I came into statistics to begin with, and that's, in social sciences, even in social sciences, you encounter calculus rather frequently, in the sense that you might be, wondering about some distribution of some variable of interest. Most commonly, best example probably given for a distribution might be IQ scores, which follows a Gaussian distribution or a bell curve, as we see here. So if we say that X is our IQ scores, it might come, frequently you might ask questions such as, what is the probability of someone having an IQ greater than or equal to, any value, let's say let's say 250, right? When it comes to integration, so we're going to actually turn this, which is a distribution of frequencies, in the sense that where you see at the top here, this middle at 100, that is the most frequent score. And most scores tend to lie, sort of within this area here. It's rather rare, of course, getting beyond 250, but technically feasible. So at the end of the day, when we're looking at something like this, we actually express this as an integral 250 to infinity of a distribution function. So even in social sciences like psychology, calculus can be seen under the hood of all the statistical tests being used. Actually, fun fact, there is at least one person in history who has an IQ estimated at around 250 and 300. He never actually had his IQ taken, but the man's name was James Sidis, and he could read the New York Times at the age of 2. So it's not this range of values is not necessarily an empty set. Okay, so to begin with chapter 4.9, focusing mostly on antiderivatives, or entirely, I should say. So, first of all, what is an antiderivative? So, definition would be a function, capital F, is an antiderivative of lowercase f over some interval I if capital F prime of x, or the derivative of f, is equal to lowercase f of x for all x and I. Now, this particular statement can be a bit confusing. So I like to personally express it in the following form. So first of all, this is in something called Newton's notation when we have a prime or a dot, but I prefer Leibniz notation, so it's like d over dx. So basically what the statement is trying to tell us is this. Now, why do I prefer this notation? Well, it actually has properties rather similar to fractions. That's why we write it sort of looking like a fraction to begin with. These are called differentials, this numerator and denominator. So we can actually do something like this. Once again, this is not technically a fraction. It just behaves in the end similar to one. So for mnemonics, or just for memorization's sake, I like to use these differentials. So that's the same thing as saying this, right? So I just multiply both sides by dx, or rather multiply. And then you can take the integral of both sides. Now, when you take the integral with respect to fx, by the way, this is also going to be, if you're going to differential equations, this style of solving or dealing with derivatives is more or less the most common way. So it is something that if you might want to get used to if you plan on going that route. So this can be actually rewritten like this. You take the integral with respect to this function. It is just the function itself equals the integral itself. This is sort of like a sneak peek into what we're going to see later, and that's that the antiderivative is the indefinite integral. But just by, while we're here already, it's a rather quick step just to get to this part using this sort of mnemonic. Okay, so for our first theorem, we're going to be dealing with what we call the general form of antiderivatives. So for some capital F, once again, we're going to use that to denote an antiderivative from now on, of lowercase f, taken over some interval I, the most general antiderivative of lowercase f on I can be written as that antiderivative f plus any constant, right, for any constant c and r. To illustrate why, let's note the following. Right, the derivative of this it's going to be the same as the derivative of fx plus c. Why? Because you can distribute this top part. This gives you this. What is the rate of change of a constant with respect to x? There's none. It's 0. So you can always tack on a constant when you're dealing with an antiderivative, right? You can always tack on a constant. When we say, and this also illustrates another point, when we speak of antiderivatives, we're looking at sort of like the pre-derivative. What is being differentiated at the top? So f, capital Fx, right, is going to be the antiderivative of lowercase f, if we can kind of express it like so. In this case, I'm trying to show that if capital Fx is an antiderivative, so too must be capital Fx plus c for any constant c and r. So moving onwards, we're going to look at a specific kind of problem that pops up rather frequently, I'd say. That would be getting the antiderivative for something that's a piecewise function. And this could be, a bit tricky because, of course, our I, which is our interval that we're looking over, is now split into two. We have, in our case, I1. Let's just call I1 right? It's going to be all the x's explicitly, so strictly greater than 0, right? And our I2 is going to be all the values bounded above by 0, but including 0 as well. Now, we're got basically what we're dealing with in this case is I being equal to I1 union I2. So if we are able to show that, the antiderivative exists at I1 and at I2, perhaps as a piecewise function, then we satisfy it over all of I, which is exactly what we're going to do. We're going to end up with an antiderivative that's itself a piecewise function over I1 and I2. And because I1 and I2 make up I, we therefore do so for I as well, and we solve the problem. You'll see what I mean in a second. Okay. So let's first do I1. So for I1, let's say, what do we have here? We have f of y. I'm going to call it y so we don't confuse it with x. For f of y, we have f of y equal to 2y. So let's look at what we have here. I'm going to do a little aside. So if you ever see brackets drawn like this, it usually means your professor is doing an aside. It's not a part of the main thing that they're trying to show you, but something that might help out. What do we know? We know that dy squared, so the derivative of y squared with respect to y, well, that equals 2y, which is what we're dealing with here. Remember what I said before, when we're talking about antiderivatives, it's like saying the pre-derivative, we're looking for what we can put on the top here. In other words, what this is implying is that f of y must be equal to y squared for y in I1. Okay, so we have it solved for I1. Now we're going to look at I2. So for I2, we have f of y equals minus x. So we're going to do something similar here. We're going to do another aside. And what can we see here? We see that d, say minus d of x squared, right? So the derivative of x squared with respect to x. Well, if we did that again, we would just get 2x. Actually, these should be in terms of y. My apologies. Get 2y, I should say. Therefore, the pre-derivative should be something that gets rid of that 2. So perhaps we should look at the following. Let me make this a bit clearer. Let's put in our pre-derivative, y squared divided by 2. So the squared is going to the y. Then what do we have? We have the 2 go down, and then it's taken out by this denominator, and then we're just left with minus y, because this negative sign goes in. All right, so that implies f of y, rather say capital F of y equals y squared divided by 2, or rather negative y squared divided by 2, my bad, for y in I2. Okay, so now we got to put this all together. We did I1, we did I2, and now we have to look at I, which is the union of the two. We're going to make another piecewise function to represent this. So what do we have all together? altogether, we have our pre-derivative or antiderivative. We have that equal to x squared, or x greater than 0, which is our I1. And we have it to x squared divided by 2, or actually the negative of that, for x less than or equal to 0, which is our I2. That's it. Okay, and moving on. This is a table of probably the most common antiderivatives you'll come across. It's pretty integral, and no pun intended, that you memorize every antiderivative on this table. It is these identities are just stuff that you don't want to spend time proving to yourself on an exam. They should be something you get right away. It could apply to problems. Especially, I would say, these trigonometric ones, which a lot of people try to neglect, probably because they're a bit tedious. You know, they're useful. They are definitely useful. As you could see, when I was dealing with antiderivatives, I kind of had to think in terms of a pre-derivative, so to speak. It's not very intuitive. It's something that you'd like to take the guesswork kind of out of it. You don't want to really spend much time deliberating on it. Luckily, if you memorize a table like this, there's no guessing. It's something that you can deal with because things like distribution, like distributivity of sums and derivatives allow you to just turn things into linear combinations, which are much easier to deal with, which was exactly how I solved the previous problem, right? Not the previous, but a few problems back. This one here. You could see this differential get passed on in this step here to a sum here. So you could think of memorizing your table as allowing you to do these kind of operations later on. So for chapter 5.1, this is dealing with Riemann sums. Basically, a Riemann sum is a way of approximating the area under a curve by splitting the domain of a function into subintervals of equal range, whereas to say that each of these subintervals have equal range. So, how does this exactly work? Well, what we're going to do is we're going to draw a rectangle from 0. So when I say from 0, I mean in the second dimension, y. We're going to draw it from 0 to the function. We can draw it to the function where for each rectangle, the right side touches the function, or we could draw it such that the left side touches the function. Which side touches the function determines whether or not these rectangles will be above or below the curve. Notice that if it touches from the left, every other point besides that which is touching it on this top edge of this rectangle, for all these rectangles, none of them are touching this point. None of them are touching, the curve. Another method that's not pictured here is the midpoint method. That's where you draw the rectangle such that the top of the rectangle meets the curve at the middlemost of its interval. So we saw the left, we saw the right, and now we're talking about the middlemost when we say the midpoint method. Okay. So here's what you know. This is calculus. This is talking about limits. What does this have to do with what we're learning? Well, we're talking now about taking these rectangles and making them smaller and smaller and smaller. Remember, these rectangles are touching each other, so each time we're making these intervals smaller, 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 until essentially we're just drawing infinitesimally small lines underneath the curve, where if you just look at it, it just looks like a shaded area. What I'm trying to say is you take the limit and it approaches the true exact area of the curve by looking at these finite Riemann sums, right? So what Riemann did was he looked at this way of approximating, taking rectangles above and below, right? And he said, why not just take the limit as these widths of these rectangles approach 0 and just get the area under the curve for, let's say, an infinite amount of these rectangles of infinitely small width. That's exactly what we're going to be looking at. First, let's focus on the non-infinitesimal widths. When we're talking about width in general, we are looking at something like this delta x. Delta x is the width of these rectangles for whichever method we're using. So it's going to be the highest value of your interval minus so for each of these intervals, they all have to share this width for them to be equally spaced. You're taking the length of your interval, right? B minus a, that's the length of your interval, and you're dividing it into n equal parts, right? So by definition, that's what's going on here. We're just going to denote that delta x. So that's going to be the width of our common interval for each of the rectangles. So let's make, I should say make, not munch. Let's make these widths infinitesimally small by sending this denominator to infinity, right? Let's look back at this delta x, right? This becomes smaller. These intervals become smaller if we split it into infinitely many parts. If we send n, the denominator, to infinity, it shrinks delta x. Okay, so let's make these infinitesimal by sending the denominator to infinity. We're going to arrive with the following, and that's going to be that the exact area under a curve is going to be the limit of our Riemann sums, right? The Riemann sum is expressed as such, right? So it's the f of xm. When I say that, we're saying the part of the rectangle that touches the function itself, right? It's going to be equal to actually the function evaluated at that point. Let's look what I mean here. Let's see here. So at this point here, we have this value here, right? Let's close xi, right? So what do we see? We see f of xi is this part of the curve, but also it's this leftmost part of this last rectangle. So you can see they're actually equal. The function evaluated xi, as well as for this last rectangle, the part that touches the curve. So back down. Right, we say that f of xm is evaluated at xm, is f evaluated at xm, right? Just like a normal function, but it's also where the rectangle touches the curve depending on which method you're using. Okay. So when dealing with Riemann sums, there's going to be some identities that you should definitely memorize, and that's all of these. You probably won't have to prove them on an exam. I know when I did Calc 2, at least I did have to, but I think it might have been uncommon. I'm not sure if this holds for UC Irvine, but regardless, even if you do end up needing to prove one of these identities on an exam, you should still memorize all of them. They're useful, very much useful when dealing with Riemann sums, and you're going to be dealing with Riemann sums. So yeah, we're going to assume for the rest of this that this is going to be in our heads. We'll refer back to it if we need be, but memorize each of these. So we're going to tackle our first question now. All right, so I know during the live session, I didn't really talk much about what exactly the terms upper and lower sums mean, but it's a bit different than just saying left, right, and midpoint. To illustrate, I'm just going to quickly draw out what this function looks like. So it's sort of like a bell curve. We're going from minus pi to pi. Let's go look at what our delta x is. Our delta x is going to be equal to b minus a divided by n, as always. So n is going to be equal to 3, plugging that in. We have pi minus pi. It's the numerator. That's just going to be equal to 2 pi over 3. So remember, our rectangles are of equal width. So starting from our lowest value, negative pi, we move up a value of delta x to get the upper bound of our first interval. So explicitly, that would look something like this. Negative pi plus 2 pi over 3. Multiply this by 3 and divide by 3. Right, so that equals 2 pi minus 3 pi over 3. Right? Well, that just equals negative pi over 3. So let's draw that in there. What you can see is if you keep doing this, you're going to get pi over 3 here. And of course, pi here should intersect with the origin. Not origin, with the or y line. Y equals 0. So we end up with 3 portions. We have an interval here, we have an interval here, and an interval here. So between minus pi and pi minus pi over 3, minus pi over 3 to pi over 3, and pi over 3 to pi. Okay. Now, if this was just the left, right, or midpoint method, it'd be pretty trivial. You just, for each of these, you take either the leftmost of each interval, the rightmost of each interval, of the 3 intervals, or the midpoint. When we talk about upper and lower sums, it's a bit different. So I'm going to use a blue pen for the upper sums, and I'm going to use a yellow colored pen for the lower sums to represent their points at which they're going to be evaluated. So within the interval minus pi to minus pi over 3, let's look at the upper sums. What is going to be the maximum value in this interval in terms of not the x dimension, but in the y dimension? So in terms of f of x, well, f of minus pi over 3 is obviously larger than the rest of these values. So we're going to evaluate our first interval at that point. So for our second interval, which is in between these two numbers, we're actually not going to choose negative pi over 3 or pi over 3. We're going to choose 0 because in that range of numbers, minus pi over 3 to pi over 3, f of 0 is the largest, clearly. And for this last one here, what will be the largest between pi over 3 to pi? Well, just like in this case, it's the mirror image. It's also going to be itself pi over 3, not pi, because pi is obviously smaller. So for the lower sums, we're going to evaluate, and I'm going to mark this with a yellow highlighter. So we're going to try instead to find the lowest values. In this first interval, well, obviously this is the lowest. In the second interval, both pi over 3 and negative pi over 3 are going to be the lowest. So in this case, I'm just going to arbitrarily choose 1. In this last interval, pi over 3 to pi. Also, let me first, mention, when I say they're both the lowest, they're both also equal, right? If you draw a line between these points, I mean to say that they're equal in this function here, f of x. So on this last interval here, pi over 3 to pi, well, f evaluated at pi is going to be the smallest. So for upper sums, we're evaluating negative pi over 3, 0, pi over 3. For lower sums, we're evaluating at negative pi over 3, or pi over 3, they're the same in this case, and pi, respectively. So we're actually evaluating this upper sum. We can do it as follows. So our formula for the Riemann sum, once again, that's going to be as follows. Well, we can plug in our n already. You can also plug this in. I'm just going to plug them in straight away. 2 pi over 3 of f of x m. And we know our f of x m's, or rather our x m's, because like I said, we're doing the upper sums, and we chose our 3 values to evaluate the upper sum at. So this is going to be equal to 2 pi over 3 times f of negative pi over 3 plus f of 0 plus f of pi over 3, right? And just plugging this into, our function up here, what we're going to end up with is simply that this is going to be, about 12.005. Right? So just plug these values straight in. The hard part was really figuring out which values to use, but maybe I shouldn't say hard, it's just not necessarily something people would know right off the bat, seeing upper and lower sums, just the terminology. But that's what it's going for, that's what it means. So let's get the lower sum. So for the lower sum, what values did we choose instead? Let's go back up and look at our distribution we drew here. So for our lower sums, those are the ones that I highlighted in yellow. You have negative pi over 3, or pi over 3, take your choice, and then pi. So noting that, I'm going to have our Riemann sum equal to, say, 2 pi over 3 times f of negative pi plus f of negative pi over 3 plus f of pi. And after just evaluating this out, we're going to see that it's approximately equal to 8.1. And there we go. We have both our upper and lower sums. So moving forward, we can now look at chapter 5.2, which is all about definite integrals. So now when we're talking about the points being used, we're going to use this terminology called sample points. Because really, at the end of the day, when we're talking about infinitesimals, it doesn't exactly matter which method we're using, because we're talking about something with 0 width, right? It's you don't get many options if you're talking about something that small. In particular, it's actually a range of numbers so small that it's for every number larger than 0, it is larger than this interval, and we're getting to something infinitesimal. So I'm not saying 0, but I'm saying quote unquote 0 when I say infinitesimal. So we're not getting many options. They're the same as far as error is concerned. So we're just going to call them sample points when we're talking about limits of Riemann sums, which is how we calculate area. So we also note that for our sample points, the first value, x0 or x0, is going to be the lower value of the interval, and we're always going to assume that the last value, xn, is going to be the upper value of said interval. Now next, we're going to discuss this term integrable. To be honest, I think a lot of people can kind of forget this. They can also forget exactly what it means for a limit to exist. I've seen actually a lot of fourth year students forget what it means for this limit to exist. All it means is that if you evaluate the function, the limit exists if it's less than infinity, right? So it doesn't diverge. But if we're talking about a limit of a Riemann sum, as we do in this case, if this limit exists, right, the limit of the Riemann sum exists, then we call the function contained here, we call it integrable. That's all it means. So it's sort of like an extension of the term limit existing, but specifically for functions that are considered with an integral sign. So when such a limit exists for an integral over AB, we say the function is integrable over the domain AB. So now here we're going to talk about some conditions that can lead to integrability. So any curve which is continuous on a closed interval or has a finite amount of jump discontinuities, finite meaning that there's not infinitely many of them. So you can always say there's x many of them, x does not equal infinity. We say, if that's the case, if we could say that about our curve, then that curve will necessarily be integrable. Not all curves have to be discontinuous. Not all curves that are integrable are continuous or have finite discontinuities, but the case of curves which do have only finite jump discontinuities or are continuous all over the interval AB are all integrable. So that's all this is stating. But note that the direction of what I'm trying to say here, in terms of which is and which isn't integrable, not all integrable curves are going to be continuous or have finite jump discontinuities, but all that do will be integrable. So it's in one direction. Okay, so here is a sort of table that should be memorized before your exam. Just as I mentioned before with antiderivatives, these are sort of things that I'd say most people, as they progress in mathematics, just kind of end up needing to know. They kind of keep it, you kind of just have it at the back of your head at all times because they're used that frequently. So memorize it now. You're going to have to memorize it eventually. And if you want to do well, you might as well memorize it anyways. I would say, though, pay special attention to this one here, because I see people forget this sometimes, and it's going to come in handy when it comes to the fundamental theorem of calculus. What it's saying here is that if you have, some set of bounds and you want it to be in the other direction for this integral, so you have b on the bottom and a on the top. If I wanted b on top instead of a, I could just switch them and then take a negative sign of the entire integral, and that's fine. That works. So you can always switch this direction, right? The direction of this of these bounds of this integral. So that's very useful. It's actually a very powerful tool that always seems to come in handy. So next we're talking about when we're comparing integrals. So I'd say here also, of course, memorize all of them. We have them in terms of the functions outside of integrals, how they behave inside of integrals. So if a function is dominated by another, so dominated meaning always greater than or equal to, then within the integrals for the same common domain, it'll also dominate. And then we have obviously this one here about being greater than or equal to 0. But I think that's most important to mention is this bottom one here. which is also a rather powerful statement. It's talking about bounding between two constants. So, these might look, useless if you just looking at it for the first time, but these comparisons become extremely useful because what is in the middle of these bounds here, right? So we're saying this integral in between these two, upper and lower bounds. Sometimes it's hard or impossible to evaluate the integral in the middle, but possible to evaluate the bounds. Let's say the bounds converge to one another, then because the middle part has to be less than or equal to the top and greater than or equal to the bottom, it must be equal to what they both converge to. All three must converge to the same limit. That's called a squeeze theorem. That becomes extremely useful. So pay special attention to comparing integrals, especially as you get later in this course. It should come in handy. So next we're going to talk about just transforming a Riemann sum to an integral. It's actually not that hard. In this case, we're doing it over some domain 1 to 3. Well, it's actually as simple as this. Sure, it looks it looks kind of tough if it's in this form, but it's actually just as simple as writing 1 to 3 x squared plus 4 dx. That's it. I know it's really hard. No, just kidding. It's obviously one of the easier questions you'd probably get if you do get asked anything about it, but it's really just meant to ensure that you understand that these two can be changed. So something can be changed from a Riemann sum form to an integral, sign form notation. They're the same thing. That's all it's really trying to hammer in. Okay, and here we're going to talk about proving that this identity works. And this kind of shows why it's important to understand that integrals really are Riemann sums, because the way to prove that this identity exists will be to transform this left-hand integral into a Riemann sum. So we're going to start with that. Okay, so just starting off, let's find what our delta x is going to be. So remember, delta x by definition is b minus a divided by n. Well, we're actually talking about, we're proving a very general statement here, so we're not going to be able to plug anything yet. So we get to use this most general form. So let's acknowledge that. And we're going to now rewrite this integral ab of x dx, right? That equals the sum of delta x I equals 1 to n of delta x times f of a plus I delta x. Why is that? Well, think back to when I was showing you the question with 1 plus cos x divided by 2. Recall that I was moving from left to right by looking at the smallest one, adding on I plus delta x, taking what comes out, right? So for the first interval, it's the smallest one plus I plus delta x. For the next one, it's what was the one we just got. Let's add another I plus delta x to it. Then we got another interval. So you keep moving on by tacking on another I delta x, right? You're moving on I times from A, in other words. So because we're progressively moving up and up in that manner, you can always rewrite or Riemann sums like this. So next up will be the fact that that our f is just simply x in this case. So that this is just really going to be delta x times I equals 1 to n of, well, a plus I delta x, because f is x. And now it's actually not too bad. We're just going to expand it out a bit. Oh, and by the way, this should have the limits. So I'm going to add those in very quick. Right, there we go. So now that we have that limit there, right, we can rewrite this. And you always have to include this limit term, because technically not including it would mean you're saying that this equality is something, which it definitely is not. It needs to have that in there. Let's actually plug in our delta x now. So that's b minus a divided by n, right, times the sum I equals 1 to n of a plus I of b minus a divided by n. Okay. Now we get to expand this sum out, right? So we can expand it to the a and I term. So this is just equal to the limit as n approaches infinity of b minus a divided by n times the sum of I equals 1 to n of a. Actually, let's do it like this. Plus b minus a divided by n squared. We could just pull that out, of sum of I equals 1 to n of I. So knowing that, this is simply equal to the limit and approaches infinity, b minus a divided by n. Well, what did I tell you one of the sum identities was, right? You have a constant, sum of a constant. It's just going to be that constant added onto itself n times, otherwise known as n times that constant, right? You're adding itself n times. So b minus a divided by n times n plus b minus a divided by n squared. And we have another identity here. We have our I. What was I? I is n minus 2 divided by 2, I believe. Or it might have been 6. Let's double check. Oh, it's 2. Okay, 6 is the I squared. Great. So, that down there. There we go. So we end up at this. Now, we have it actually now entirely in terms of n and constants b and a. Our goal is now to take this and let's see if we can get rid of this limit, right? We're going to simplify it to the point that we can get rid of this limit. So this limit as n approaches infinity. So let's try that out. Just going to copy this and put it onto the next page. We can continue where we left off. Okay. So knowing this, right, what can we do here? Well, that n cancels out there, so that's the same thing as saying b minus a, right? That n canceling out, the limit of a constant is still that constant. So b minus a plus b minus a n, well, we're going to have this n squared here. It's going to take out, this n is going to take out one of those n's. So we're going to end up with 1 over n b minus a squared n minus 2 divided by 2. So we're going to end up with this. We can simplify this further, obviously. Though it seems that I need to add back in our limit because that limit does not disappear for the right term, only just for the left because the left is two constants. There we go. That limits for our friend over here. I also realized that this should have an a because we had a times n. Let me just quickly correct that. So that should be, I'll put the here, this one. Right, because I was saying sum of a constant is n times that constant. So I just kept the n, forgot the a. I added it back in there. So knowing this, we're going to now try to get rid of our n's here. We could rewrite this as the following. Let's try taking all of our constants and putting them together. So b minus a squared divided by 2. And put our n's together here. Because the limit, product rule of limits and constants, you can just ignore these constants here and move the limit to n minus 2 divided by n. All right, now we're just working with this guy here. What do we see here? N divided by n, that's 1. 2 divided by n, as n goes to infinity, well, that's 0. So we can just get rid of it. Well, it's going to be 1. So there we go. Any other simplification, I'll just kind of leave up to you. But this is now just simple algebra from here on in. There you go. That's how you get rid of the limit. And turn this into a problem of a constant. So just through some algebra, you're going to be able to get it to this. I'm going to add the question mark there because you really should expand it out and get rid of the terms, but just to save a bit of time and not to be stating the obvious, I'll leave it at that. All right, so moving on, we now are talking about the fundamental theorem of calculus. Let me just fix that there. Fundamental theorem of calculus. The most important theorem in calculus, by probably agreed by most people, I'd assume. It really does tie together derivatives and antiderivatives, and what we mean by saying an antiderivative is the same as an integral. You'll see why in a second. This first one here is the derivative linking part. So we have g of x equals so lower bounded a, upper bound x, integral of ft dt. All this is saying is that we can sort of look at integrals with the function upper bound as a function themselves. Sorry, like with a variable upper bound as a function of that upper bound itself. This does, however, require continuity on a to b and differentiability. Once again, this is linked to differentiation on the open interval a to b. Remember this, closed, open. That could be a tricky thing at times, and it really does make a difference. You can't, you can't do this with merely open interval for continuity. But here's the very powerful part of this statement here. What this tells us is g prime of x equals f of x, right? You take the derivative of an integral like this, you take the derivative of that, it's just the same thing as plucking out this inner function, right? And just saying evaluated at its upper point f of x. Notice that uh, we're differentiating with respect to x. We're differentiating with respect to the bound, not t, the bound. So if your upper bound is not x, but let's say x squared, you're going to have to use the chain rule if it was x squared instead. So that's an example there. FTC2. So this is the part linking antiderivatives and saying it's the same thing as an integral. Notice, of course, at the beginning of our discussion, when we talked about what an antiderivative was, the first thing I did was relate it to an integral. This is probably the more formal statement, right? Especially with, I linked it to an indefinite integral. This is talking about evaluating a definite integral, so with a lower bound and upper bound. What we end up seeing is you take the antiderivative of the upper bound, subtract it out the antiderivative of the lower bound. So all that stuff with Riemann sums that we have to worry about, with this theorem here, FTC2, all it's saying is we now just have to turn it into a problem of finding what the antiderivative is and then just evaluating at the bounds. So very, very powerful statement. So we're going to do a nice example here. First, remember the identity I told you to pay attention to earlier about switching the bounds. Now we get to use it right away. We're going to find the derivative of capital F, but our x is on the bottom. Minus f of x equals 0 to x, 1 plus the secant of t dt. Right? Of course, I could just take the negative and put it on the other side. That'll probably be a bit easier to work with. Right? Now, let's take the derivative. Right? It's just as simple as evaluating it at x. Yeah, that's it. Right? The only trick was to remember the identity. It turns out actually a lot of calculus turns into, did you remember the identity to use in this case? But that's really just a sign of calculus being this very mature system that we're able to make books and and tables of rules of thumb to make our lives simpler. So now we're going to talk a bit more about indefinite integrals, which is literally just talking about antiderivatives again. So once again, the notation, I actually showed this part a bit earlier. Right, I showed that I was related to the definition using the Newton notation, changed it using Leibniz to basically say this. Well, just using what we saw before, this is just the same thing as saying that if we have our antiderivative, taking a derivative of an antiderivative, which is kind of the same thing as inverting the inverse of a function, turns it back to the original function, right? Turns it back to f. We also have something called the net change theorem. Basically, all it's saying is that, first of all, when we're saying rate of change, right? That's what we usually, when we're referring to a derivative, we're saying that it's the rate of change of a function with respect to x. So all this is saying is the area of rate of change, think of it like that, right, is just simply going to be, it's evaluatable at the non-derivative version of f, right? So f itself, fb minus fa using ftc, and we're good to go. We can, like I said before, ftc2 just makes it very easy to evaluate definite integrals. Using FTC, all we have to do is find out what these antiderivatives are, and we don't even have to touch Riemann. We don't have to actually touch the Riemann sum should we use the right tricks and tools and memorize our common integrals, which brings us to this very, very, very important table, the most common integrals. Memorize this as always. I would say also make sure to pay some special attention to these ones here, because they pop up when sometimes maybe you're dealing with something that's not trig related at all. Like you're just dealing with polynomials, and then all of a sudden it comes to a form like this, right? Well, you can turn it and you can always simplify it using inverse tangent, inverse sine. So compared to the rest of these, where the trig just kind of involves other trig in terms of the left and right hand side of these identities, this one changes a polynomial type of type of problem into something involving trig, which can actually make your life a bit simpler. You can work in either direction, of course, right to left, left to right, but pay special attention because I'd say this one tends to slip by due to that reason, that they're sort of like in separate fields. All right, so now we're at chapter 6, at 6.1, and we're going to be talking about our substitution rules. Right? So we can use the relation that we got from our FTC to derivatives to make integrals much less kind of like guess and plug in work. One way of doing it is note the following, right? So I'm using here differentials like I used at the beginning of this lecture to sort of show this out here. Let's let a be equal to some integral of fu du. Well, let's see what we can do here. U is just, a variable, so we can just do, let's say, just as x could be as well, we can multiply and divide by this differential dx, and, just simply moving the dx over, du over dx, we have the derivative of u with respect to x. Let's just substitute u equals g of x for clarity, and we end up with a being equal to this over here, f of a function times the derivative of that inner function, right? That becomes pretty powerful in either direction, of course, but it's because sometimes you have a derivative that might simplify things. Take the derivative of x is 1, right? Obviously, that makes that dealing with that a bit easier, but the main thing to keep in mind is sometimes differentiating can take a big thing and shrink it smaller, especially for powers. And there's a few other ones we're going to get into as well. So we should also note the following here. It's related to remember I was talking before about the variable bounds of an integral? In this case, it's actually relating it to what we just saw before, the last slide, to do with U substitution, and specifically with respect to bounds. If you have your bounds as functions of your upper and lower bounds, respectively, you can transform it into what we have here on our left-hand side, right? Needless to say, that is probably very useful when your bounds look messy, right? So it can also be used in conjunction with FTC1, right? We talk about taking a derivative of the integral itself, but yeah, the main thing is if you notice a function, the same function existing for both your upper and lower bound, just take out what was on the outside there and stick it in as you would a uh, as you would in U substitution. And by the way, the term U substitution is used usually because uh, usually when this is described for the first time, it tends to be with du and u inside, but uh, it's just generally substitution rules. There's a few different terms for it, but I think a lot of students will call it U substitution. That's what this is. So for this function here, we're going to try using U substitution to make our lives a little easier. We're actually going to learn an identity in the process of this, and that's going to be the following. We have 0 to pi of any f sine of x times x dx. This is always going to be equal to pi over 2 of the same integral, 0 to pi of sine x dx. Okay, so that's quite interesting in of itself, I believe. So the actual way we're going to prove this is by using the following substitution. Let's say, let's let u equal pi minus x. This will allow us to also just say simply that x equals pi minus mu. But it also implies the following. So these are implying that dx equals minus d mu. So in other words, I'm taking the derivative, right, x prime. Actually, I'll rewrite this in a nicer way. Because you probably see people skip to that notation a lot. I know it used to bug me. What it's saying is following. So just take the derivative dx over du equals minus 1, right? Because you do that. And this is actually probably the first application of the differentials that I was using before, the sort of algebra of differentials I was using earlier, that you normally see in a calculus course, or in any course really, because now what you're going to do is multiply both sides by the differential du. That's how you end up getting things in this form. So this will imply that our left-hand side of this thing here is going to be 0 to pi. What was our x? It was pi minus u. F of sine pi minus u. Right? And our dx is now going to be equal to minus du. Let's pull the minus sign out. Leave the du in. So that's how we get to something that looks like this. And now we can move forward with noting one thing. Do this little aside here. Sine of pi minus x. You can see actually that it's going to be equal to sine of x just by periodicity. Okay, so that allows us to simplify this inner term over here. And now really all that's left would be to get the rest of it behaving. Let's just write that out. And to do that, we're going to, or rather actually, we first need to note the following. Our bounds of integration here are not going to be 0 to pi just yet, because we have something interesting here. Our bounds are now in terms of u, not x, right? So we're going to have to find u of pi and u of 0 as the bounds, right? As it turns out, and for the second one, I'm actually going to plug it in. It turns out that this is just 0 to pi, right? Where's our favorite identity again? Well, that allows us to switch this by just taking the negative sign out in this case. Therefore, we can go back to 0 to pi and get rid of the negative sign. So now moving forward, let's move actually into a blank page. Second. There we go. Just copy over the last line from the previous page. Okay. That should be a pi. Seems to have lost its little leg. So let's expand this out. See the following: 0 to pi, 5s sine u du minus 0 to pi, f sine u du, and that should be u f sine u du. Now here's something interesting. We're kind of back at square one here, right? We were trying to show a property about 0 to pi x of f sine x dx, right? This should actually have its own bracket. So all that we did was switch u for x, but we can see right now that's the same thing otherwise, right? They're both variables in R. So we can actually see the following. Let's go back up to our previous page. Let's call the left-hand side here, right? Left-hand side 0 to pi x f sine x dx. We're going to call that, I'm going to give it a name. We're going to say that the left-hand side is equal to I. Then what do we see here? We actually see the following. When you evaluate this integral, that has to be equal to I as well. It's recursive, in other words. You'll see a lot of this when you do something later called integrating by parts, when you see these sort of recursions like this. But we're going to see it a little earlier with this u substitution problem. I could just call this one I. So we could say this. Well, let's simplify this out a bit. Let's add this I to this side, right? And then we can divide by 2. So that's going to be the same thing as saying, right, I equals 0 pi f sine of u du divided by 2, right? We could just put that 2 underneath in there. We could say that we got what we needed. So remember, this is a two-part kind of question, I guess. This is an identity we're going to use. So we're going to keep that in mind. We're going to keep in mind that we can basically get rid of the x attached to any function of sine and change it into pi divided by 2 when it's under an integral 0 to pi. So let me make another page here. So just get a little bit of time traveling to the morning, but let's finish this up here. So now we have our identity. We could finish this up. Apply it right away here. So remember, that gives us 2 pi in place of x in this case. So 2 pi 1 plus cos x in this sense, or cos x squared. Now we can do a bit of a u substitution. So just a bit of an aside. We're going to say u equals cos x implies that du over dx equals minus sine x. In this case, of course, we can multiply both sides by dx, and then we get our expression for replacing dx with du. So now it's important to realize one thing here. You can kind of get an expression for a du without having to plug anything in here, because if we multiply this whole thing by -1, then -1 sine x dx is going to be du. So what I'm trying to say is the following. And then let's say minus, and we're going to multiply this whole thing by -1 because, of course, we want to undo the minus as well. Keep this equal to itself. Minus sine x dx, right? This here is equal to du. Let's make that a bit clearer, though. There we go. So this here is equal to du. So when we're replacing all of this, you can also see the following. Actually, this maybe I shouldn't have it evaluated at cos yet, so let's close pi and 0 still. The next step will be, because we're going to say that this is equal to -2 divided by pi, cos of 0, cos of pi, and now we're going to actually plug in our du, so we get to get rid of this. Right? So instead of x, we're going to have the inverse in this case. So we'll say right? Right? So this can be rewritten as 2 pi, right? For the first one, it's going to be pi over 4 minus, I'm going to bring in our minus sign of pi over 4. And we get the final answer that this is equal pi squared divided by 4. Right? So we did a couple of substitutions across basically a question and a half, and we get our answer as below. So continuing onwards, right, chapter 6. Okay, so just moving forward, now we're going to be talking about the area between curves. Of course, we have here, I think it's rather simple. It's pretty much what we've read so far, except we're just combining two different curves and subtracting it out such that the area that's left is only what is in between. Right, so we're going to move on to this rather simple question here. We're going to find the area between these two curves. Just moving here. We're going to see that this is a case that we're going to want to integrate with respect to y because of, we're seeing it's moving such that we have one curve on top of another curve, but only in the x direction, whereas we usually expect in the y direction. This will make things simpler. So in other words, we're going to be subtracting out curves. So in the x direction, this curve, this parabola, it's for higher values of x, right, instead of y, if we flip it this way. So it's on top of this y equals x curve. So we're going to want to integrate in this sort of direction, where we're going to be subtracting this out from there, but we're going to be doing it with respect to y. The integrals are going to be dy. So let's see some things here. First thing to notice is, let's plug in y equals x into this, right? So 4y plus y squared equals 12. This becomes a polynomial, right? So we can just factor this out. It'll turn into y plus 6 and y minus 2, right? So that'll give us our bounds of integration, because these are the zeros. So our bounds for integration are going to be minus 6 to 2. All right. So from this, let's first see what we can do here. We can now set up our new integral for the y direction. What we see is, firstly, that we can actually just say, let's simplify this one here. We'll have, in this case, we're going to have x equals, so we're going to divide it by 4, and we're going to move the y to that side. So we're going to have x equals 3 minus y divided by 4, right? And what does this give us? This gives us two equations now entirely in terms of y. So we can now integrate the area between the two. So remember, when we were talking about area between curves, we're just going to subtract one from the other. We're just doing this in the y direction, so we flip it over. So it's going to look just like this. So our top curve is this parabola, and our bottom curve is this y equals x. Of course, in this case, it's just going to be y dy. So now it's just rather simple. It turns into this linear combination. Applying the antiderivatives should arrive at 64 divided by 3. I won't really go into that just because it's rather trivial, but the main trick was being able to turn this into dy, whereas we usually deal with dx, because now we're flipping the whole thing over. Do a little question mark there. Make sure to fill in those blanks. So now we're going to be talking about the surfaces of revolution, which allows us to take a 2D object and kind of project it into 3D space, just by kind of rotating it around. So, right, our curve in this case is going to look a little something like this. We get square root x, kind of juts out like that. And we're essentially just rotating it around this y equals 0 line. So, like that. We're going to have the mirror of that in the bottom. And this is how I usually draw surfaces of revolution. So I just look at the top part, I mirror it underneath, and then you can just draw these sort of half circles in between to signify that it's solid. It's a sort of wireframe, right? And at the end, I'll just cap it off there. So we have this surface here. It's projecting sort of into this three-dimensional space, but we're actually just dealing with a two-dimensional object. So it's sort of like cheating our way into something more that we'll explore in Calc 3. But for now, you can already deal with three-dimensional objects. So yeah, we're going to note this over here, right? So that because we're revolving our x, right? Or we're revolving our function about this line where that's where this pi comes from. Right? It's revolving, and specifically, it's such that this is referring to the area of a sort of cross-section cylinder. So let's just draw out a little cylinder here. We're going to sample one. Let's say some cylinder here, right? It has, it's obviously 3D, so let's make sure it wraps around there. Doesn't look quite nice, but get rid of the one next to it. There you go. Here's our cylinder. This, we're trying to take it's like a cross section. So we're trying to take the area of the cylinder and make sure actually I call the whole thing in, because like I said, it's a cross section. And what we're seeing is the area of a cylinder with width delta x. We're saying that the area is going to be equal to, so this entire yellow shaded region is going to be equal to this AX, right? So what this is just trying to say is that if we take cross section out of this with, that with any arbitrary width delta x, that the area of that cylinder is going to be equal to this, pi x times that width, right? Because you're just sort of extending the circle in a cylindrical kind of way, right? And we're only extending it by the length delta x. So just lastly, let's actually plug in here what we need. So in general, the formula for finding a surface revolution will be, or the volume of one, will be V equals, well, we're plugging in our bounds here because we're looking at 0 to 1. AX dx. We have our value here for a cylinder of width delta x. So in other words, it's going to be equal to 0, 1 pi x dx. Notice here, actually, this delta x, we're seeing it kind of turn into dx, and that's really one way of thinking about what a differential is. It's like an infinitesimal change in some value. So difference in x, you can think of it as very small difference in x's. They're related concepts in that regard. So this is rather easy now. We can just plug in, we just evaluate this antiderivative. Remember, is one of the identities. It's actually the first antiderivative we looked at was with regards to 2x, the piecewise function with 2x and minus x. Well, for the minus x, remember that I had to find the pre-derivative by simultaneously also dividing by 2. Well, this is just that thing again, but at this point I memorized my table and I see constant times x here. I know I can just turn it into this right away, just apply it right away. Apologies, I got excited, I guess. So from this, we get our simple pi over 2. We get our answer. And last but not least, we're going to just quickly acknowledge the mean value theorem, which is really it's an intuitive concept. It's the average of all infinitesimally small intervals over our interval a b, right? That's what's going on here. We have the so we have the length of it. Then we have the area. So you can think of it as the average applied across the entire interval. It's rather simple, but it does help with proofs here and there. I'm not going to spend time just kind of going over it because really, at the end of the day, it's just a theorem to memorize that tends to, you know, pop up if you're doing a proof. I guess like I'm trying to think of when I did this course, I think I did get a question exam about it, and it was merely just to state it. But I can say, obviously, as time goes on, that I see this thing pop up every once in a while, and sometimes it slips my mind. I said, oh, why don't I remember that thing from Calc 1 I should remember, or Calc 2? And yeah, that's more or less what this is. It's memorize it, and really just be able, make sure you're able to state it, especially. So that covers this review session. Once again, feel free to ask any questions you may have in the Discord server. It's a pleasure being able to teach you. I, of course, love this material. I'm happy that I got to go over it again. Fun to be able to do